Cool. 982 triple. Excuse me. Triples with bitwise and equal to 0. Man, that's can interpret in so many ways. Okay. Given an array of integers a, find the number of triples of indices. Is it a triplet? Anyway, triples of indices ijk such that they're all within the index. A sub I and bitwise n, a sub j. I assume bitwise a sub k is equal to 0. Where n with okay. That's interesting. Okay. So the nodes also hides, or at least I can tell you all the they don't put up in front. I think at this point, at least for Leetcode, I recommend looking at the notes first because it gives you the constraints that you could do. And clearly, I mean, this is a hard problem. I imagine as such. And if an n cube algorithm worked, then it shouldn't be hard. It would just be 3 for loops, right? So I didn't imagine that would be. There's 16 bits and 1,000. So I think in theory, an n square algorithm can run in time. But yeah, cool. Now let's kind of figure out how we want to do this. I think again, the first thing I would do is doesn't seem like we need to care about the order. So I think the first thing I'm going to do is just sort the array, just to give it a structure. As we said earlier, I fully expect the algorithm, and some of this intuition, I don't have anything to back it up quite yet. I have to think about it a little bit more. I'm talking out loud. But my intuition is that it's going to be n squared somehow. And we saw it, it's just n log n, so it should fit in the n square space. Or like, it gets dominated by the n square part. So it's all n squared now the case. So why not sort it, right? Cool. Now let's kind of think about this, right? So I think, so each element can contain 16 bits. What does that mean, right? Is that there's something that we can kind of take advantage of the fact that it's 16 bits? What to say? I think my initial thought right now is to think about whether I could do some kind of caching to kind of help build up some sort of lookup table for memorization type thing. But I still feel like maybe it still degenerates to n cube, so I don't think that's really a viable avenue. But you know. So the answer could be n choose 3 at most, or maybe not, or n cube maybe even. Oh no, just well, yeah, n choose 3. What is? I think yeah. I think one thing that I think about, or that I was thinking about, is kind of calculate what n choose 3 is, and it seems to be 166 million. So that's cutting it close, especially with overhead, and also maybe I misread that number. So like, no, because n cube is a billion, right? So it's strictly less than that. Hmm. Oh, actually, I was wrong. This is actually n. It's not n choose 3. It should be n cube because you actually I and j could have, or like, yeah, two of the numbers can have the same index. Hmm. I think a little bit. So okay. Oh, oh no, this is in Python, but oh, yeah, I mean this is in Python, so but I mean I could use Java if you want. I'm relatively language agnostic as long as I Google a lot. But also, welcome to the chat, Joe Wells Grewy. Don't if I'm messing up. I mean it's yeah, but I mean yeah, it does kind. I mean it has class and stuff like that, but I don't think it. You know. Um, hmm. I think one thing that I'm thinking about is kind of trying to construct a way in which we could have some sort of lookup table. Yeah, if we could, um, yeah, we could figure out a way to uh, kind of get the third index in a linear time, then, or sorry, in a constant time, then we could keep it quadratic. Um, yeah, I mean, I think the solving for two indices thing is kind of trivial. So that's why, I mean, it easier. So I don't, or like try to figure out if there's a way I could generalize it, and maybe in general, but um, mm, yeah, we'll take a quick look because I think given so what I'm thinking about now is that given two numbers, uh, is there a way to represent uh, because there's some sort of I think I'm thinking of something along the lines of kind of set merging, where because there's only 16 bits. Um, because there are only 16 bits, you can imagine. I mean, and this is not a fully thought out idea yet, but you can imagine that you have a list of stuff that you could avoid certain kind of positional ones and so forth. Um, hmm, think about that though, like kind of almost like removing candidates one by one in a recursive way. Um, can that be done quickly? Hmm. Um, a million up. Right now, I'm just thinking about kind of the complexity of the things I'm doing. About let's say we have like a million candidates, which we would have for n square. Uh, um, let's say we have a million candidates. Is there a way we can go through candidates, each of those candidates, very quickly, or like the remaining index very quickly? Um, but the problem is set mode. Actually, maybe that could work. Because okay, so this is what I'm thinking right now. so because of it's 16 bits, you can imagine we just create 16 arrays, right? 16 elements, and each of those elements represent one bit that maybe it's still too slow. But yeah, so I was thinking that yeah, so you have 16 arrays. Each of them represents the list of numbers where the numbers are 1 or maybe 0. But and then you kind of do some kind of set merge operation to kind of figure it out. But that's still O of n for set merge. So looking here, also there's a lot of duplicates, but I'm not sure that that helps us that much, because I mean, so essentially it still would be n choose 3, except for you know, there's a factor, a multiple factor of, you know, how to kind of, I guess actually it's n choose 3, and then you take that number and then you times it by, you know, the combinatorial way to kind of count that number, meaning it could be 1 or 6 or something like that, or 2 or 3, something like that. But that's a kind of a constant time linear, a constant time optimization. So I'm not kind of sold on that quite yet for now. But yeah, maybe Johnny one man has kind of the right idea. Maybe we should solve for 1, 2, and 3. And choose 3 is 166 million, right, or something like that. Am I okay? 1,000 choose 3, that is. Can we do 166 million n operation fast enough? Okay. Maybe I'll try to do the naive things just to kind of see what kind of runtime we're cutting across. I think it's not going to run, but why not? It's worth a try. Oh yeah, so you definitely at least need 2 numbers, because one number by itself will always be non-zero. So let's do it. Nope, that's not right. What am I doing? Yeah, if 2 numbers create a set, if you will, how many ways can there be, right? So let's see. Oops. So there's can be, let's say A, B, and there's 3 ways to do this, and then fly in my face. There's 3 ways to do this, so it should be just count you as 6. I'm happy with that. Actually, this would be true for the input minus maybe. Yeah. So this should give me 6 on the standard input. Oops. On the example 1 input. Okay, that's expected. Also, I think there's a you could do it in other tools to do a combination, but I don't know right now. So let's do a quick optimization. I guess actually. But I suspect that this will not run in time because otherwise it should not be hard. But people do not like this farm. I don't know what that means yet right now though. This should also give you 6. Okay, so this will probably get this farm right, but whoop, spoke too soon. Oh, man. Also, this could be optimized a little bit, but that's, let me see first. Man, I forgot about the farm statement. That's interesting. I mean, actually, I think I messed this up a little bit, but because this is already, if this is already true, every K will give you, so, that's actually interesting. So then, and is he gonna say something like that? And then each of those has 6, so something like that. But we may be double counting in the future, but okay, at least for now that looks okay. Oops. Let's now try to do the 3 index one. Typing is hard. I mean, this still shouldn't change the results. I think what we need to test is, well, I mean, what we really need to test is way too many numbers, but at least for now we'll do something like that. Okay, well, now let's stress test this a little bit. I really don't think it's gonna work, but okay. I was not counting, which is actually kind of lazy on me, but okay. I mean, let's see how many elements that was. Whoops. So that's just 510, and it takes 844, so that's not good. Though now we might as well stress test the whole thing. Okay, so at least we know that the just for loops will probably not work. 7 seconds. I mean, it actually finished. But I think when you submit, it actually probably times out. But yeah, well, but I can't imagine this is it either. I mean, maybe it is. All right, well, fine. That's just YOLO. But Hmm. Yeah, actually, oh well, okay, fine. I actually had some things around. I wish it tells us my one time and stuff though, but okay. Um, I definitely did not consider cases of zero, which is my bad, I guess. Okay. Hmm. Oh yeah, because I, I said earlier that when uh, uh, yeah, I said earlier that we will not have cases where we have just one number. It could be, but it seems like, well, that that's not the case when that number is zero. So we just have to do a quick zero. Then you just count one. I mean, I don't know. Don't know how I feel about that hack-ish thing. Oops. Whoops. But it should be okay. Man, I hope I don't have to implement this in, well, actually, I mean, I guess I could just redo this in C and maybe that'll be faster. Time to exceeded. Oops. Which is kind of expected. All right. I'm feeling a little bit lazy today, so I'm just going to see if I could do it in C and make it fast enough. Okay. And if it's not, then it is what it is. But, okay. Yeah, I know. I'm using Go brackets sometimes. And there's only one instant for each of these numbers because, yeah, that is just like a trip set. Yeah. Okay. This and is good. Oops. Okay, size minus. Oh, also this is wrong. Fine. Oops. How did that happen? These auto brackets. What did I do differently? Okay, well, I wish I saved that other quiz. I guess I could actually just do this. Oops. Let's see how much faster or not it is. Oh man, 2 years to go still. Don't have semicolons in my finger memory yet. That's interesting. Wait, what? Huh. Everything is int, so what is the issue here? And everything should be under a billion. Did I not initialize something? And just 1,000 elements, whoops, or more than 1,000 elements. So that did overflow, whoops. Okay. I didn't count it, maybe I should count it. This will probably either have the same one or, only 349, man, I'm really bad at counting. But that fits in 4 milliseconds, so let's see, so if we double it, then it should be 700 elements. Man, I really hope that using C is not good enough to solve this problem, because then maybe that explains all the not likes. Okay, so 964 and it wants in 4 minutes. Well, maybe it's the zeros. Yeah, because we okay, maybe because it never triggers here, so. Yeah, because it never triggers the third for loop, that's why. Okay, let's try. This is not the worst case. Still haven't counted this. But hopefully the printf will tell me. Okay, well, it's good that it wants fast because it's wrong. So, what did I do wrong? Why is that wrong? So this isn't doing anything, but why is it not? If this is the reason, then I'm going to be unhappy. Yeah, so one thing about which I, in some languages and clearly C, the equality has a higher precedence than the bitwise and, so I have to add, I have to add the parens there. That's the, yeah, I mean, it is what it is, but I should have, yeah, I mean, oops, some of these is just weird, but okay. But I would also say that's actually a kind of a cute thing in that, like, it's not something, I mean, I know that I solved that part or fixed that part really quickly, but to be frank, a lot of it is just a lot of painful experience of making the same mistakes in the past and learning from it. So, so if you saw me like solving that quickly, don't be afraid. It's just me being. It's from experience that like I made the same mistake time and time again, so that's why I could diagnose it quickly. And also, as I was saying before, I'm actually really sad that C is good enough to do this in n cube. I mean, there's some optimizations there. So we did go from n cube, which would be a billion operations, to n cube, or sorry, to n choose 3, which is still n cube per se and O of n. But in terms of actual numbers, n cube by itself is a billion operations for 1,000, where n choose or 1,000 choose 3 is only 166 million, right? And some of that you could further kind of optimize a little bit, and because of all that and using C at once in time, which is something that I'm not happy with, maybe I'll read the discussion later to kind of figure out what the another alternate solution is, or maybe there is, and I don't know, because maybe that's why people are sad about it. But I think the only other thing that I would point out is, and maybe that I didn't, and it's and I didn't explain this very clearly, just kind of because I also, to be frank, didn't expect this to work and was expecting to do something harder. So I kind of broke them down as actually Johnny One Man kind of alluded to, but and I was kind of reluctant about it, to be honest. But I broke it down to like 3 pieces, right? One is what happens if I, J, and K have the same index? What can trigger that? And some of that we actually got the wrong answer to. I just forgot or didn't, not forget, I just didn't realize that, or didn't think hard enough around that just having 0 as an input would throw things off. But in that case, that is the only number in which, the only number in which both I, J, and K is the same number, and it's still with bitwise and 0. And then I do the checking to see what if 2 numbers bitwise is 0, and that's what this chunk is for. And I just kind of have a further optimization which gets it down from n cubed to n choose 3, or yes, strictly n cubed, not O of n cubed, but from n cubed to n choose 3 is to kind of make this 6 times faster effectively by noting that if you have if the indices are 1, 2, 2, then as we point out, or let's say A and B, I guess we'll just use I and J in this parlance. That means there are a couple of ways to do it. So the I, J, and J. This means there are 3 distinct ones, and you could kind of, I mean, there's 3 distinct ones. I guess for the sake of clarity, I'll just list them all. It's I, J, and J, J, I, J, and J, J, I, right? And then equivalently, there's I, and J, which also 3, right? So that's why there's 6. And so that's kind of one way to do it. When you have 2 numbers that bitwise and to 0. And then this part is just that, well, if I and J bitwise to 0, then any K would also bitwise to 0, right? And in this case, there's 6 permutations of, just 3 factorial, right? So that's why I did K times 6, and the number of X is you go to the remaining A size minus basically just the remaining numbers that are after J, right? So that's kind of the breakdown. And in this case, excuse me, there's a little bit of optimization in that I cached number here so that we don't do that AND operation, the bitwise AND operation again. I mean, that probably will slow it down. I mean, not probably, it will, just because it's doing more work. So here, and as I pointed out before, order of precedence. Make sure you kind of I mean, you don't have to know it, but just if you see something wrong and something's a little weird, just have a look out for it. But this is a very simple for loop, and the count add is plus, and you go to 6. It has the same reasoning here. It's just I, j, and k, and there's 3 factorial way of doing of ordering 3 items, and then I just kind of sum them together. I think I'm gonna do some research on this problem before I kind of have a have an opinion about this. I think, I mean, if this is all that there is, and I'm not sure that's the case, to be frank, then it's a really bad problem in that, well, if the same algorithm, I mean, I know that I didn't make certain optimization in Python, but just having it in C means, and I mean, and this one time is faster than like a random problem in Python, or random one test one in Python, right? So yeah, I mean, so in that case, I clearly don't like this just because there should not be language bias, and also in a weird. I mean, and I guess there's some optimizations that I've done here, but I don't think that's something that like it's very useful in like analyzing a candidate. There's nothing that I learned other than how to optimize certain for loops and stuff like that, which like when you start, right, when you unroll loops, and I mean, and it's fun and all, but I don't learn anything about a candidate, so I actually would not like this problem. If that's on the assumption that this is all there is to this problem, I'm not sure, and hopefully I get proven wrong. And to be frank, I'm a little tired today. So I got injured, just put everywhere, so I'm not gonna like, maybe I would have thought about it more, but I think for now I'm gonna just call it a day. But I think for this problem, as a result, not really a fan, but we'll see. I mean, maybe next week I'll give it a talk and kind of figure out where it is. Yeah, I mean, yeah. Constant time optimization should not be kind of what we look for in candidates. Like, we're trying to test problem solving skills, and I don't know. Okay, cool. I mean, I don't think there's that. I mean, I already went through the problem. I don't think there's anything really interesting on a depth level to this problem. If this is the only way to solve